All right, thank you very much, Mandar and the Prof. here. That nice introductions and invitations to this great place. And this is my actually first time to India and first time Mumbai as well. And I'm very much impressed by the all things happening in this area and also this institute. And it is my great pleasure and also honor to deliver the public lecture as a first Infosys the invitee. And you know that whenever you invite it as a public lecture, it's always kind of, there's excitement as well as burden, because to try to explain something that you're working on by your heart to the people that do not have the background, but it's kind of why we are doing this one in the excitement. So I'll try my best to deliver my excitement onto the research that I'm working on, why actually I'm excited about, why actually I wish you also got excited about. All right, so let's start from the title of my talk, that's saying the stacking atomic layers and the quest for new materials in physics. So there are a few words that I want to explain throughout my talk. The first part is this part of the stacking atomic layers for the new materials, and that's probably a good starting point that I want to kind of explain. In fact, the atomic scale of the materials, or this layered materials, is actually quite common. I mean, we all know the atom is very small, and expect that how to just kind of experience such a small length scale easily. But to tell the truth, that everyone here that probably have cell phones or computers in your bags and in your pockets, that already contains the technologies that require atomic scale of the engineering. So think about the computer chips. Probably you rarely open up these computer chips, but you may always wonder what's inside of these computer chips or cellular phone chips or semiconducting device. In modern semiconductor device, if you just open it up, it's made of the silicon, but it's not just as simple, but it looks complicated. So you kind of open up this cover of these chips, you see that the silicon dies contains many, many components there. Often that component is so small, so it's very difficult to see that with the bare eyes, but with the help of the microscope, especially electron microscope, you can just zoom in. And you start to see that this is not a simple object. It's a rather complicated object with many, many layers. It's like the sum of this complicated series that a lot of the layers in there. And if you zoom in there, there's another structures. And if you just zoom in there, there's another structures. You have to zoom in quite a bit, probably 10,000, 100,000 times. And then you just reach the really core of this silicon chip, which is basically what you call the transistor. And this transistor is, of course, made of the mainly silicons, but there are a lot of other structures. There's metals, and there are different parts of the materials it contains that make this small elements, what you call the transistor, whose basic action is basically turn off and on as a switches that control the electricities passed through this underneath of the layers. And the size of the transistor has been shrinking down over the past centuries, almost half centuries. And there's the law that we call the Moore's law, telling us how we can just make this transistor size small and small. It turns out approximately every 2 years, we will just kind of make this size of the transistor is about half, such that over the past years, we make this transistor size from centimeter scale now down to something like a 10 nanometer length scale. And 10 nanometer is about 100 atoms width, right? So if you just look at this, the main part of the transistors even further, it looks like now you need a really fine structures of the highest resolution of the electron microscope just to take the look. And indeed, the core part of the transistors, now if you just zoom in up to the atomic length scale, and all this little dot is basically atoms made of silicon and silicon oxide, which is basically glass, and which actually make the dissections. But you start to see that the length scale that we are dealing in this device is already down to the atomic length scale. So to make this type of the silicon works in your pockets, or the transistor works in the pockets as computer chips, we have to know how to deal with those kind of atomic scale of the length scale to engineer things in there and study them, right? In fact, our technology got evolved even further. So not only the silicon, so if you just make a little bit faster device, some of the cellular phone chips can be made of the other than silicons, like the gallium arsenide, that's another semiconductors. But whole length, the point here is now we know how to make the type of the structures, really small scale in controllable way, such that with this so-called molecular beam epitaxial techniques, one can create this silicon wafer or the semiconducting wafer about 10 centimeter size, where if you zoom in, all this layer by layer of the control can be made throughout the very careful techniques. And this is the essential technique that we need to use to create the modern days of the semiconductor chips that allows all this electronics we enjoyed can be enabled out of this type of capability. Now, these are all the engineering. I'm not going to discuss about too much of the engineering, but I want to take this as a spot that once you just acquire such the high capability or higher the ability of the controlling the engineering down to this atomic length scale, what kind of new things, what kind of physics we learn, or also how that use that physics back to again that's making something useful and interesting. So that's kind of main part of my story. So let's start with the physics that we can learn from those kind of the really atomic scale of the length scale we can have the controllability. So the physics story that I want to go back about 150 years ago. And starting with this man, the Professor Edwin Hall, who was the chair of the Harvard physics professor back then in around 90. But when he did his PhD in the Johns Hopkins University, he did the following interesting experiments. What if that you make the certain materials very thin and apply the electric currents into the thin materials and apply the magnetic field on that materials? What is going to happen? In 150 years ago, it's about the time that James Maxwell just come up with this, the summarizing the achievement of this Maxwell's four equations to describe the electrodynamics or electricity and magnetism, how that works, was discovered around that time, right? What Hall was interested in is, say, under this theory, applying the magnetic field, we exerted force onto the charge, moving charges that deflect the charge motion. His quest is basically, can I detect this deflection of charge motion under the magnetic field by carefully measuring the voltage across the current directions. So he set up the following instruments. Basically, he has some conductors here, sending the current through this conductor and applying the magnetic field in the vertical direction of this conductor. And then deflection of the charge, presumably electron, will happen, and then you can carefully measure the voltage across the current directions. One should be able to measure this minute force of the deflections under the magnetic field by just kind of this measurement. And this is what we call the Hall effect nowadays. So what he did is basically set these things up. He used thin materials and just apply the current, applying the magnetic field. There's a deflection force, what you call the Lorentz force, will deflect the charges and accumulate the charge into one side as positive and the other side as negative, and will create the voltage drop and can measure this type of the voltage drop while sending the current and make the ratio between that the voltage to the current, what you call the Hall voltage, can be measured under the magnetic field. And obviously, as you increase the magnetic field, there is an increasing of the Lorentz force, and there is more voltage developed happens. In other words, this Hall resistance will increase with magnetic field. If you just simply solve this type of the relation out of the Maxwell's equations, and then you can realize that indeed it's a Hall voltage, Hall resistance will linearly increase the magnetic field, and this is something that he measured, and now it's called the Hall effect. And this Hall effect is one of the important properties one can use to measure the charge or property of the charge, especially how much charge is in there throughout this type of simple measurement. One behind the story, however, here is following. When Hall tried to measure this experiment, he tried various different type of conductors. And it becomes quite obvious this conductor that he has to use should be very, very thin. Otherwise, that amount of current flowing there, you don't generate enough the Hall signal to be able to measure in the technologies in the late 19th century. So you may ask, what is the thinnest material he could use in 150 years ago, right? I know this is a popular lecture, but I can ask you guys, right? Can you imagine what is the thinnest material one can come around about 150 years ago?
Gold.
Yes, it is gold. So the people know how to make the very thin leaf of the gold back then. So he used about the 1 micron thickness of the gold, about 100 times thinner than our hair size, right? And that's how we know that can make this type of the technology back then. And using the very thin leaf of the gold, he barely manages its signals and just to kind of do this nice measurement. And of course, afterward, people know how to make these thin materials in various different ways. One of the ways is actually using semiconductor. Exactly the silicon technology I was mentioning about the semiconductor chips. It takes another 100 years. And to come up with the new measurement actually appears using semiconductor under the very strong magnetic field. About 100 years later, when semiconductor technology got started evolved, and people know how to deal with this semiconductor very carefully, this person who gave actually public lecture about 2 years ago, I heard, Professor Klaus von Cleaving, actually did following experiments. Simply take just computer chip that I just mentioned, so-called this silicon CMOS, complementary metal oxide semiconductor chips, and apply the strong enough magnetic field using the superconducting the magnets, and just measure the same Hall effect. And the original, his motivation is to just try to look at this so-called this in the extreme quantum limit and what is going to happen, right? And then he uses silicons and using this gate electrode that I mentioned and applying the voltage on the gate electrode, you can just accumulate a very thin layer of the charge layer on the surface of the silicons. And he just kind of apply the magnetic field and measure the whole measurement. And we expect more or less a thing like this, and the slope will give us information about giving the information on how much charge accumulated. In fact, when he did this experiment, by surely just completely surprised that he found the result is not like this, but something like this. It's increasing, but not continuously, but it's rather discontinuously with some steps. And now this effect is being called the quantum Moire effect, and certainly that this is quite a unique behavior. First of all, that we know that this quantum mechanics really goes on in these problems. Part of the reason is the hallmark of the quantum mechanics is something discrete, and this size of the step actually appears precisely, but certain kind of rules there, and this kind of discretely appears that really smells like the quantum mechanics plays an important role. And not surprisingly, this effect can be described by the quantum mechanics. In fact, that the foundation of the explanation of this quantum Moire effect comes from the 50 years before its discovery. The Landau at the Soviet Union back then studied about how the quantum mechanics dictate electron move under the magnetic field, and simply solving Schrödinger equations that discovered a few years before he studied about this problem. Simply that in quantum mechanical law of the charge motion under the magnetic field can be explained in the following way. So think about this whole bar that we send the current, and I just mentioned that the voltage across developed across these current directions due to the deflection force of the magnetic field. But if you just look at this the current flow through this along this direction of the current, if you really carefully look at this charge motion in there, it's not simply just kind of straighten off. Because of magnetic field, it's just kind of circulating around, so-called the cyclotron motion is happening, right? And the drift along this kind of current direction, and that's how this current flow. Then, of course, if you apply the quantum mechanics, what quantum mechanics will do is basically quantize the cyclotron orbits into this kind of, can be described the wave functions that around this quantized motion. Right? And the quantization of cyclotron motion will basically quantize the orbits such that within this orbit, there's the set number of the set quantity of the magnetic field can be trapped in there. What you call this flux quanta is trapped in this circle. And that's basically what Landau tells us. And how many actually the magnetic quanta is trapped in there is, of course, discrete numbers we can count may actually explain that discrete steps of this the quantum Moire effect what Professor Cleaving discovered. In fact, the better way to describe all these things is using so-called quantum wave functions, psi, that just described here. Usually is complex number where there are two quantity follows. One is its magnitude, which you can find described in terms of real numbers, and the other one is this phase, which describes this phase of the complex number. So using that concept, basically we can explain that why there's a step appears in this the quantum Moire effect. Basically, this quantum wave function that I just described, describing this the quantized orbits, has the phase. But in these steps, there is some regularity, right? The first step, if we call this is the first step of the height, second step appears about half of the first step, and third step appears is about 1/3 of the first step height, and fourth as 1/4, and so on, right? So there's certain regularities that, or more precise, there's some integer numbers actually hide into this interesting the behavior. Where this integer number comes from? That integer number, it turns out, if you just look at the quantum mechanical wave function describe the cyclotron orbits, the phase angle will just kind of circulating around when electrons, they make this one cyclotron orbits, and how many times of this phase angle circulating around this the cyclotron orbits will just give us that integer numbers, because the winding of this phase angle must be integer number. So if it is one wind of the phase angle, that's 1, correspond to the first step. If this phase angle wind around twice when the cyclotron orbit happens, that's 2, and winding number 3 becomes third steps, and so on. So that beautifully explains that why there is a discrete steps and why the step is so exact, because that underlying the mathematics related with the quantum wave function dictated by this integer number, which actually is completely discrete and precise, right? This tells us that interesting lesson. Once you get down to such a thin limits, that we start to see the interesting physics actually appears, and this interesting physics is related with quantum physics, which actually related with the discreteness of this nature, right? And you see that this is also an interesting part of the phase of the wave function plays quite an important role to understand this type of the intriguing physics there. It turns out quantum mechanics dictate another interesting phase, and that's related with so-called the quantum spin of half. We know that electron is a charged object, and most of the condensed matter physicists are dealing with electrons because they are dictating the electronic property of the materials we are dealing with. Electron as a fundamental particle has a few different properties, and one of the important properties is spin. And classical way that you can describe the electron spin is electron is charged object. You can think about this sphere is basically electron, and you can just turn around these spheres and make these spins there, and that will just kind of create a circulating electrical current around here, which will create its own magnetic moments, right? In this classical picture, of course, this magnetic moment can just point out any directions, any three-dimensional directions, right? So you can think about this magnetic moment as a vector that I need 3 components to describe about this magnetic moment directions, right? But what is a weird part of this electron as a quantum mechanical object? It turns out to describe this 3-dimensional vector of the magnetic moment, you don't need the 3 components. You need only 2 components. In other words, even if this magnetic moment is pointing in the x directions, in horizontal directions, somehow quantum mechanics dictate that I can use up and down only just 2 directions to describe about this direction in the x direction, right? This is a little bit weird. Think about this 3-dimensional object, but I need only 2 components to describe that. In fact, this 2-componentness actually provides yet another very interesting and intriguing property onto the electron spins. That's a related following statement. So if I just have the electron and describe the electron's quantum mechanical state with the electron, the wave functions, it turns out when I just turn around the electron 360 degrees, it actually comes back almost its own, but with some difference, with negative sign in front of this wave function, right? So this is a really weird type of things. It's something like that you just watch me, and then I'm just turn around the 360 degrees, and it's come back to me, but for the, if it was an electron, it doesn't come back to its own, but has a negative sign in front of it, right? But since this is a negative sign, I know how to get rid of it. How? I just turn around once more, then I have another negative to negate this one, right? That's precisely what happens to the electron wave functions. It has to go through the twice of the turning to get back to its own. If it just turn around once, basically it just kind of have this weird negative sizing in front of it, right? And this actually related with some of the intriguing topological structure, in fact, right? In fact, you can just create a very analogous mathematical object doing this one. That's actually Mobius strip. Probably you just once try to make this type of weird strips. If you just have this strip of the paper, instead of you just connect them to make the band, if you just twist it and just connect them, this is a way that we can make this Mobius strip. And there's one intriguing factor about this Mobius strip. Imagine that I have the electrons that sitting on the one surface of this Mobius strip, right? And just kind of carefully just turn around the electron along this path and turn around 360 degrees along the surface of Mobius strip. You will find out electron will not come back its own, but direction of the spin is opposite even if you make the 360 degree turn, right? Same way that I just described. However, if you make another turn, then it's come back its own, right? So precisely this starts to tell us electron spin actually carries some of the intriguing these topological structures that relate with this type of the physics, right? Now this tells us quite an intriguing part. So electron spin is a very weird in a sense that it has kind of some interesting phase properties. In fact, this can be generalized together with what I just mentioned about this quantized orbit. And generally, in quantum mechanical object, this type of the phase argument either relate with these orbits under the magnetic field or the ideas of an electron spin that turning around carries all these quantum mechanical phases can be all described by the so-called Barry's phase, which actually written by Sir Barry's about 30 years, 50 years ago now. That describe about this intriguing the quantum mechanical nature of the phase of the wave functions described in such a way. And once you have this electron in such a way, it could be quite intriguing. However, you start to see that there is a kind of two discrete stories I just mentioned. One is basically phase of the wave function on the magnetic field, right? Create these orbits and the magnetic field flux that encaptured by this orbit. And the other one is the electron spins that I'm just turning around. That sounds like the two completely different objects. Indeed, it is two different objects under the non-relativistic quantum mechanics, right? We know that in the beginning of the 20th century, there's two important pillars of the physics. One is a special relativity developed by Einstein, and the other one is this quantum mechanics developed by many people, but I just write down Schrödinger, who just wrote the Schrödinger equations. In this non-relativistic quantum mechanics described by Schrödinger equation, the quantum mechanical spin that I just mentioned about the electron is just kind of add-on quantity, right? You describe everything about the Schrödinger equations to describe the orbital motion, as we just discussed about this Landau's quantization problems, right? But then spin is just add-on. But deeper physics actually was discovered soon after the development of the quantum mechanics, when Paul Dirac just tried to combine these special relativities with non-relativistic quantum mechanics, try to write down this completely relativistic and quantum mechanical equations, now called the Dirac equations. It becomes clear, in fact, the spin is kind of deeply related with the charge motions as well. According to the Dirac's equations, it turns out when you just kind of accelerate the particles or charged particle, more precisely spin, half particles, the level of the speed of the light, then there is an intriguing connection between the spin and its velocity, or the momentum more precisely can be made according to the Dirac equations. What happens is that more direction of the spin should be either parallel or antiparallel of this momentum direction, whether it becomes particle or antiparticle, right? And this deep relation is quite intriguing, because now spin degree of freedom is not in a sense just completely kind of free, but somehow it's deeply tied with this momentum direction, where the electron moves, right? So how to prove this type of this intriguing, the property of the relativistic particles? Well, one way is basically going to the really large system, the particle accelerators. Because as you see here, that only when you accelerate the electron up to the speed of the light, this property can be seen, right? But imagine that if you have the Large Hadron Collider and you accelerate the electrons in there, and what you expect to see here is, according to the Dirac equations, this particle or electrons, the spin direction will be tied with its momentum directions. So whenever electron is moving around this gigantic rings accelerate with the speed of the light, close the speed of the light, then the spin is actually tied to its momentum, such that when electrons is moved once, it's go back to these negative signs in front of it. It actually have to go to twice to get back to its own wave function states, right? Unfortunately, this is a very difficult this measure, the wave, kind of this change of the minute wave function differences in such the large scale of the experiments. Then what can we do? Well, here comes kind of interesting trick of this so-called condensed matter physics I have been working on. So condensed matter physics is dealing with the materials. And as you see the materials, as I showed you in the transistor as a good example, if you just zoom in, there are many, many atoms, many, many electrons, right? Usually about 10 to the 23rd, the electrons, ions into this small area of the cubic centimeter of the materials that we are dealing with, right? So it's complicated, right? But over the probably 100 years or so, condensed matter physicists have developed how to describe the complicated system one by one in quantum mechanical way, right? Especially the materials I'm going to tell you today is based on the somewhat simpler system. If you just look at the periodic table, there are many elements that can all participate into the rather complicated system. Let me just take the one simple example as a good starting point. And that simple example I want to choose is carbon. And carbon, part of the reason is that we're all made of the carbons other than the water, right? And carbon is number 6 elements in this periodic table. There are 6 electrons can participate in all this chemical bond. But turns out the 2 electrons basically locked in the core and 4 electrons make the chemical bond. There are a few different ways to arrange of these 4 electrons that can make the chemical bond. The one way to make the arrangement to make the chemical bond is so-called sp2 carbon bond. Now, this is a rather complicated terms that the chemists use, but if you look at this simple diagram, you probably notice that you've been seeing this type of molecular diagrams before. This is benzene molecules, that there are 6 carbon atoms make this chemical bond, and there's a hydrogen atom is decorating outward. But if you just notice each of the carbon atoms, there are 3 chemical bonds to make the chemical bond to its nearest the elements, right? So each of the chemical bond per carbon atom will just cost 1 electron. Then since I mentioned there are 4 electrons per carbon atom can participate in the chemical bond, there's 1 electron per carbon atom can be used for something else. And often this is 1 electron, so what you call the pi electron. It's just hovering around all different carbon sites, makes so-called delocalized electron networks there, right? So as I said, the carbon is basic elements that consist of most of these organic molecules. And whenever you just look at the organic molecule, you can think about the following way. Each of the carbon atom donate 1 electron can slushing around this network of the hexagons. Basically, this is a physicist's view of how to look at these organic molecules, right? It turns out there's one generalization you can quickly make this kind of organic molecule even bigger. The way that it just can do that is you can make this either saccable-like shapes or the long one-dimensional shapes or two-dimensional shape, or even just make the stacks of the 2 dimensions and so on. Turns out all of these elements or all of this, the materials actually has a name. Of course, the graphite is something that we are most familiar with. But also, over the time, people just discovered not only cartoon, all of these materials actually do exist. In the 80s, the chemists actually found that these fluorines, what you call the buckyballs, that consist of the benzene type of the molecules that connected together make the spherical form, right? In the 90s, that the scientists in Japan just discovered that the extended version of the fluorine into the straw type of this network of the carbons in what you call the carbon nanotubes. Actually, I did my PhD onto this carbon nanotube in 90s, late 90s. But then people just realized, Well, those kind of systems also tied with the graphite, their basic elements describe all these materials, which is basically one single atomic sheet of the graphite, what we call the graphene, is basic materials to describe all of them. In a sense, starting with this 2D atomic sheet of the graphene, if you stack them together, you get the graphite. But if you just roll this graphene up, you can get the nanotube. Or if you just kind of fold this graphene up, you can get the fluorine. So we know that these are all kind of connected, but the elements of the most important part is the graphene, right? So in the early 2000s, just after actually I got my PhD, I just mentioned that people already knew that there are kind of intriguing these connections of those kind of carbon materials. And then natural thing you can ask is how the electron can move inside of these materials. It turns out they're applying the quantum mechanics to this system. You will find somewhat intriguing features. So look at this graphene network that I just mentioned. Just let me zoom in one of the units of this network, which is basically hexagons of the carbons, right? But if you stare at these carbon atoms carefully, you can recognize that you can categorize or classify this carbon atom, 6 carbon atom, in 2 different groups. Let me just paint them as one red groups and the other one as blue groups. And red versus blue groups, their chemical bonding structure is actually opposite, right? So take the red atoms and flip it around, you get blue atoms. So there is a so-called inversion symmetry is there. So how to describe the electrons moving inside of this network of this the chicken net type of the carbon network? The quantum mechanics tells us that there are the bases you have to set it up. And of course, these bases can be naturally set into the red carbon atoms versus blue carbon atoms. And right description of this quantum mechanical description of electron is basically so-called the quantum mechanical superposition of these two, right? So you start to see sense of this two-componentness, right? This two-componentness, that is something that I use to describe the electron spins, and they have the very intriguing, the phase relation, Betty phase actually comes around, precisely can be analogically constructed into this type of this network of the carbon. Hence, to describe the electron wave function in here, basically you need a two component, and how you add up or quantum mechanics impose this kind of two component becomes important. So there are very analogous description of this spin type of description appears. What you call is the pseudo spin description of this the quantum mechanical wave function of the electron in graphene. One can take this a little bit more seriously, and already in the 60 years ago, when Philip Wallace, the Canadian physicist, tried to describe the electron motion in the graphene, or graphite back then. He just come around, in fact, solving the Schrödinger equation to describe these wave functions. You will get the very similar structures, what Dirac equations that describe the electron at the relativistic limits can be analogically described into this type of the quasi-relativistic descriptions, describe this charge motion in the graphene. And there, basically, again, that spins of, or more precisely, pseudo spin of the electron is tied with deeply with the direction of the electrons on the circulating around these band structures. So all these things start to tell us somehow the analogical, the quantum mechanical, relativist quantum mechanical description becomes very important to understand the charge motion into the graphene. So that basically adds up to another excitement. It's not only the graphene, the two-dimensional sheet of the carbon, is important elements to understand that what how all this low-dimensional carbon materials actually works. But on the top of that, in the physics-wise, we actually expect something interesting things happen due to this analogy of this charge dynamics in the graphene to the relativistic quantum mechanics. So that was the situation around the 2000s. Already the physicists and chemists and material scientists working on these carbon materials start to realize, well, that might be interesting. That work on the graphene, you may actually discover something. So that's precisely about the time that I actually just got the PhD and completed 4 postdocs, and then I start my own lab at the Columbia University back then. And I decided maybe this is interesting enough problems I want to work on. Right? So the first thing then we have to find out is, okay, so we know that graphene actually can exist and may show this type of interesting behavior, But then next question is, how can we create the graphene sheets, right? Well, in 2000, nobody knows how to make the graphene. But we know that graphene can exist inside of graphite. So the idea that we had with my first year students of the Yambojang was the following things. Since the pencil made of the graphite, and indeed if you just look at under the microscope, electron microscope, the pencil lead consists of these stacks of the graphite, right? So when you just kind of grab the pencil, write on the paper, you will probably cleave on some of the little piece of the graphite, or maybe some perhaps in graphene. So that was the idea that we started with. So the first generation students in Yambojang was kind of courageous enough. So we discussed maybe instead of this macroscopic pencil, what if we just made this small scale of pencil called the Nano-Pencil. So Yambo actually went through that kind of following procedures. First, he just carved it down, the chunk of the graphite, into make the small pieces. So using the microfabrications, he made this kind of little blocks of the carbon, something like the micron size, right? And then take this kind of blocks of the carbons and attach it onto the AFM cantilever. And this is about the 10 times smaller than your hair width. So you can see the really, really tiny nano-pencil can be made in that way. And then grab this cantilever that where graphite blocks in that they attach it, and carefully scratch it onto substrate to hope that some little piece of the graphite, hopefully the graphene, can be deposited onto the substrate. And this was a really wild idea. However, it actually worked. He carefully just cleaved it off, and those thin crystallites actually cleaved it down, and we just can wire them up, just electrically probe that under the magnetic field, measure the Hall effect. We start to see that this quantum oscillation start to appear, tells us that indeed quantum mechanical action is happening in this very thin sample. Back then, Yambo and I went down to about this 5 nanometer thickness of the sample, which consists of about 10 layers of the graphene sheets in there. Right? So it was not the single layer that we aimed, but we were very close because, well, we're starting from about millimeter size of thick graphite and now get down to the same something like the nanometer. So we went down about 6 orders of magnitude, and we just left one last order of magnitude to get down to the graphene. So around 2004, when we just kind of get to our first result, we got so excited, we started to write the paper. And then about to submit the paper, and then we heard about the rumor. And saying that, well, you know that we are not the only one that doing this crazy type of the experiments. And soon after we just submit the paper, we saw the preprint coming from the other groups, actually, that describe very similar physics. And that was the paper done by Andrei Gaim and Kostya Novoselov and the University of Manchester. And this paper, when I just read this paper, I got shocked, kind of couple of shocks, actually 3 shocks more precisely. The first shock is, of course, oh gee, that we got completely scooped. And that was actually 2 years of our hard efforts. And that was my almost first experiment we did. And it was not a good feeling, right? And you worked some things for 2 years for your hearts, and especially first experiments, you got completely scooped. And it is completely scooping. Part of the reason is I just told you that we went down to about 10 layers, and still we have a 1 order of magnitude to get down to the really ultimate limit of single layer of the graphene sheets. And these folks actually get down to single sheets and do the experiments. And the very similar experiment, the result we got. So our data is basically subset of their data, right? Okay, so good. So we got defeated. That's fine. But the next thing is then how they actually get this single layer, right? I mean, we just come up with this elegant idea of the nano-pencil. There must be something in there, right? So when we just kind of carefully read this paper, we got the second shock. And the second shock comes from the fact that they use really simple techniques. Anyone work on the graphene or heard about the graphene probably heard about these scotch tape stories, right? They literally use the scotch tape many, many times and get down to the really thin layers and deposit onto their substrate. Such a simple techniques, completely scoop us, right? That was our second shock, right? And third shock comes up a few years later, and they actually got the Nobel Prize out of that work. So that was good. But back then, Landau was really disappointed, not because of Nobel Prize, but because we got completely scooped out of 2 years of the work, right? And it was such a simple techniques. And then we just kind of decided, Landau, go and get this sketch tape into the stationery store in front of our school, and let's try out whether it works. Actually, it worked. Within a week, we create a single layer. This method is now well established, and you can even find out the good recipes in the YouTube, and you can do it in your kitchen, indeed, literally, if you have the piece of the graphite. Using the sketch tape, you can just successfully peel it off. You can get the single down to single layers. You can just kind of find out that with not sophisticated things, but simple optical microscope, you can actually find out the single layer with the eyes, right? And if you use carefully using AFM, atomic force microscope, you can measure, indeed, they are just one single atom unit cell thickness of materials. Thinnest materials we can get rather simply, right? Although this is a rather simple things you can get, of course you can make the device out of it, and from that part, you need to go through the all so-called microfabrication techniques. People often use making the semiconductor chips. Using graphene rather than silicon, you can make the device and start kind of study about their properties. And then if you just do that, you'll find out quite intriguing things. Part of the reason is, from the beginning, this is just one atom thickness of materials, is completely quantum mechanical materials. First thing you notice as intriguing physics is following. If you measure Hall effect under the magnetic field, how this deflection of these charges happen. Not surprisingly, they also show this stepwise increase. Just ignore the blue things, but focus on red one, which is Hall effect, right? You start to see the familiar steps. But then you notice that there's one difference. This step size, I mentioned that first step is 1, second is 2, third one is third, and this half and 1/3, fourth that appears. But the step size doesn't look like that level. It turns out first step size is half, that one is 1/6 and 1/10, and that's a step size. In other words, if I call this 1, next one is a 3, and the next one is a 5, right? So if I just kind of put these numbers, step appears a 2, 6, 10, 14, and what is next that you expect? 18, right? How to generalize a number? 2, 6, 10, 14. It turns out that number is a 4 times of this half integer, right? That's a difference from that what I just kind of mentioned about semiconductors. Something intriguing things happening here. What make those kind of things as appears a half integer rather than full integer? It turns out that physics is related with something that I mentioned up to now, right? I told you in the graphene, basically there's a pseudo spins that describe there's a kind of red and blue carbon atoms, right? And these two componentness actually create something like the spin-like the structures, what you call the pseudo spin. And the other part is, well, electron moving inside of the graphene sheet more or less mimic the Dirac equations, relativistic, the quantum equation, quantum mechanical equations, which means that when I just kind of send the electrons around and make the cyclotron orbits, like the electron moving the Large Hadron Collider at the speed of the light, right? It just kind of carries these pseudo spin directions along these momentum directions, and you just spin around, right? But then you have to think about another component I mentioned. Well, pseudo-spin carries, pseudo-spin, like the real spin, carries its Barry's moment, Barry's phase, which means electron has to turn around twice to go back its own, right? So precisely those kind of fact that you have to turn twice to get back on means if you just turn around once, you only turn around half of the turn, which means instead of we have 2 pi of the angle, you got the pi of the angle. And that's precisely the reason why we have this half integers. Basically, incompleteness of the rotations coming from this Barry phase tells you about these half integers. So what you see here is such a simple system that you can just get a very intriguing and deep physics all together with kind of all this kind of interesting way. But not only just the deep physics that we just kind of interested in, turns out this graphene becomes quite important materials for the future applications. Again, graphene is highly conducting materials. It's so thin, so light can go through. As you see in the microscope, you can see there's this faint colors. But also, the carbon network here is a very strong network. Therefore, it has a kind of very intriguing or very high quality of the mechanical properties, or it conducts very well. All of these properties or combinations, actually people have been thinking about using this material for the various different type of the applications. I'm not going to touch upon all of these things really carefully, but certainly over the past 15 years, people got really excited about using graphene as the application materials based on the atomically thin system. But another important aspect of the graphene research, as a good example, is a very first step showing that how one can get very atomically thin materials. It turns out it's not only graphene. Nature has provided us many different materials, atomically thin, can be possible. So graphene out of graphite is a good example. Now this thin layer materials, that there's a hexaboron, it's like the graphene-like the materials, but instead of carbon, it's made of the boron and nitrogen. Turns out this is good insulators, often is called the white graphite. You can also thin it down to monoatomic layer. There are a whole slew of the materials called the transition metal dichalcogenide, some of the oxides, some of the organic materials, inorganic materials, but nature gave us that many materials that all this chemical bond is within the layer, and between this layer is weakly held like the graphite, such that using the Scotch tape you can just peel them off one by one. Not only using the Scotch tape, over the time people actually have developed a way how can grow this material layer by layers in larger scale for the applications. Another exciting part is, unlike the graphene, which is just kind of good conductor or intriguing conductor, turns out that different materials actually have different electrical properties. Some of them are semiconductors, some of them are good superconductors, some of them becomes magnetic. There are all sort of different type of material quality appears by choosing different type of host. And the other exciting part is because they can actually cleave down to one single atomic layer, or they can grow down to one atomic layer. In principle, you can just grab them and just put them together again, right? So stack them together in the different order to make this so-called heterostructures out of it, right? So in this type of the possibility, we can imagine following things, right? You can just kind of make the stacks of the system all consist of different layers. So this is electron microscope, not a joke, but realities. One can actually cleave it down to all different materials, and you pick them up one by one and restack these three-dimensional structures. However, each of this layer now consists of the many different type of the materials, right? Now you start to see that there's stark comparisons. Compared to this MB grown sample that I showed you semiconductors before, right? Layer by layer control of the growth. Now, very similar way, we can just kind of make this system layer by layer. But the big difference here is each individual atomic layer can have the different functionalities. Why this is more exciting? The part of the excitement comes from that all this ingredient that we are just dealing with can have the different electronic properties. And yet, you can just stack them together to make these quasi-3-dimensional structures with a different type of the functionalities. And indeed, in this type of the functionalities, in terms of application, we can gain a lot of the diverse application. One can make the very fast transistors. One can make the very sensitive the optical sensors. One can make the light emitting diode, ultra thin the photovoltaic cells, biosensors, and all of this, because it is atomically thin material, they are naturally flexible, so you can make them as not the rigid electronics, but make flexible electronics. So in terms of application, you can see that starting from the graphene, diversifying the materials in the very different 2D materials, there are a lot of possibility you can simply opens up for the new applications. But rather than dwelling on this, the many different applications we can just set up, I want to kind of end my stories going back to the one intriguing another physics stories out of the enabled by this type of the stacking atomic scale materials. Not only you just kind of choose different materials to stack. By the way, if you choose the same material, you can make that rather intriguing structures. Here's a good example, right? Let me just take the two graphene sheets, but just kind of stack them together. But when you stack them, not only just stack kind of in the direct way, but what if I just kind of give some of the angle difference? This is so-called the twisted angle difference. But although I just kind of stack two graphene layers, you start to see that end result looks quite different, right? So there's complicated patterns appears, but if you just carefully look, there is some regularity appears. And this regularity is what we call the so-called Moire patterns, usually appears when you just bring these two similar materials together with some of the twisting angle, right? Do we actually expect something intriguing things happen in those kind of structures? In fact, actually, somebody think about those kind of intriguing structures that usually comes around so-called commensuration in commensuration problems. And somebody was Douglas Hofstadter, who actually wrote a very influential books called this Godel, Escher, and Bach, Eternal Golden Braid. And that was one of the million sellers in the late 70s, early 80s. And in this book, actually, he described a very intriguing part of the connections between these Godel's incomplete theorems with Escher's painting, with the music of Bach, and then that's kind of all kind of intriguing connections in terms of cognitive science. I don't want kind of describe everything about there because it's intriguing and interesting books, but also kind of beyond the my descriptions that in short talk. But at least I can just give you some hint of what he was describing actually can be well captured by this nice book, nice painting done by the Escher. And this Escher's painting is called this the relativities. And you see that most of Escher's painting, it's rather intriguing. It's just basically, if you follow through this and it's going up or going down, but it comes back, it's almost like feeling of the Mobius strip that I just mentioned is there. And most of the Escher strip actually tells us something like this intriguing part of this, the geometries. And another intriguing part is this, the Bach's music that actually, all right, so I think, well, I cannot make this animation. But if you just look at the Bach's, these canons, or called the endless rising canon, you can see also very intriguing, this kind of circulation, but it's not just kind of simply repeating, but there is a kind of intriguing, the structures appears on the periodicity. And that's all kind of related with all this Hofstadter's claim about how to make all these connections in the cognitive science way. And the reason that actually he got interested in actually dated back to his PhD work. Turns out the Hofstadter was actually physics major and got the PhD under the guidance of this, the 1 year to get the PhD in the theoretical condensed matter physics, the describing about the commensuration in commensuration issues in his thesis. And in fact, in his book, he just plotted out this so-called G-plot, which actually direct from his thesis. And this is basically energy and the spectrum, energy spectrums of the electrons moving under the magnetic field in periodic electrical potential. It turns out this problem is exactly hit these issues of the commensuration in commensurations. Later on, when you apply this magnetic field and just associated quantum Moire factor appears in, it turns out all this, the energy spectrum is deeply related with some of the structures that appears into this quantum mechanical, quantum Hall effects. It looks rather complicated structures, but if you just look at these structures carefully, there's some of the orders there. It is in fact actually fractal structures. The self-similarity appears in this type of the spectrum. Well, fractal, as we know, is complicated, but there's hidden orders. Turns out that hidden orders can be described by the two integer numbers that relate to this. When Hofstadter actually wrote this book in the late 70s and early 80s, that this type of the description only remains in the theoretical world, and experimental realization was quite hard. But when it comes around, this type of the graphene sheets, or the 2D layers with the twisting angle, one can actually create the very analogous problems and apply the magnetic field. One can start to see the intriguing quantum Moire effect appears, that something like this. This is a magnetic field and this is density. You start to see that your Hall effect, the magnetic resistance actually shows a rather complicated patterns. If you just draw these patterns, turns out it can be all described by the integer numbers again, but except one integer number that describes simple quantum Moire effect, you need two integer numbers precisely related with this, the Diophantine equation describe this Hofstadter's spectrum is exactly appears there. So this is another example. By simply just stack these atoms together, one starts to see that this beautiful physics, or more precisely, beautiful mathematical structures also appears in experimental proof in this kind of system. Also tells us that what kind of intriguing physics we can just kind of learn from this type of the atomic stacks that we can create it. Well, I would say this is just beginning. I just mentioned there are many different types of the two-dimensional electron system, right? Simply just break down these electrons or growing this system, you can come up with many different types of the two-dimensional atomic layer. Some of them are metal, some of them are semiconductor, superconductors, magnets. What kind of things do you expect when you just kind of put them together, right, in this dissimilar metals, dissimilar materials? What kind of things do you expect when you just change their stacking angles? And these are all kind of not largely answered problems we are actually working on to understand the physics behind of that, and as well as some of the useful devices one can realize out of this type of the combination. That's basically the end of the stories. If you want to learn a little bit more about this physics as well as the device aspect, I would invite you that tomorrow I'm giving another seminar, but this is, the tomorrow's seminar will be a little bit more professional, so I will just use more of the physics jargons there, but at least kind of you can get the sense what kind of things we can learn or what kind of things we can just make out of these atomic stacks together. I hope that I just kind of deliver enough the excitement that we have in this system, but with this I will end my talk. Thank you.